Hey. Oh, hold up. Are you on mute or something or what? Your headset's not working.
Oh yeah.
There it is.
There we go. I was on mute. It's such a funny video. Oh my goodness. King of wishful thinking.
Let's see this video.
That you'll hear in a department store or elevator music.
Oh.
It's so old.
Let me clock in.
Hey.
I submitted my timesheet, sir.
Oh, I already submitted them.
All right.
Don't mess around. It's easier than effort certification.
Yeah, I finally got taken care of. Jesus.
Oh, it's the worst.
Do you have that like FortiFend or whatever it's called?
Yeah,
like,
yeah. It was on my school laptop, so I have to, yeah.
I have to put it on my personal laptop. I wasn't too happy about that.
Yep. That means Vista. That means Alamo Colleges now owns your laptop. Man, something's in the air today. My allergy meds. My allergy meds are not working today. I've been sneezing all day.
I feel like my eyes have like cats scratching at them. Like they're so itchy. It's so bad.
Right? I think today's real bad.
Yeah. Like the rest of like my nose, it's not really bad, but my eyes are just feeling it hardcore.
Yeah. Like my left nostril, like every time I breathe, it's like, I don't know. It's like
rattling.
Yeah, rattle, sting, and then I sneeze, and I'm just like, oh, like, come on.
I'm the same here. I've blown my nose so many times now. Now I've hiccuped because of it, and it won't stop.
Oh man, yep, the worst.
I hate Mountain Cedar so much.
But like, I've been loading up on allergy meds, allergy steroids, Flonase, and then if it's really bad, I go with the inhaler. But it seems to be working until today. I guess Cedar's really high today. I have no idea.
Let's see. Cedar count.
Cedar count. Where is it at? Forecast. What pollen is high today? Ragweed's high. Or no, low. That's low. What's this? Facebook. January 10th, 2011. What? That does me no good. Mountain Cedar is at medium today.
Yeah.
Don't feel like it. Mountain Cedar is moderate. Got it. Oh, okay. Oh, it's 5 o'clock. Welcome back, everybody. Any questions before we get started?
I have one, but I'm trying to find what number it is.
All right.
I know it's 1.3.
Come on, computer.
Can their project be on the math behind a mantis shrimp?
Ooh. Yeah, sure. Deal.
Those things are cool.
All right. What number?
It's going to be 1 second. 11.
11. Sketch the graph of that piecewise function. Okay. Let's look at that. 1.3 Okay, 1.3, number 11. It has 4 plus x, where x is less than -1. X squared for -1 less than or equal to x less than 1. And 2 minus x for x greater than or equal to 1. Okay, and all I want you to do is sketch this graph. So one of the easiest ways is you can make an XY chart for each function. So if we looked at the first function, I would make an XY chart for that. Y equals 4 plus x. And the restriction tells us what numbers to pick. So this says we have to choose numbers less than -1. So I'll start at -1, and then I'll go less than. -2, -3, -4. Probably don't need any more than that. And then you'll take these numbers and plug them into that function. So 3, 2, 1, 0. Okay, but we have to make note of something, that we can't actually use this point because the restriction says we have to be less than -1, not less than or equal to -1. So that means this point will be undefined. Good so far?
Yes.
And then we'll do this function, which x and y equals x squared. And this one says we can only choose numbers between -1 and 1. So I'll have -1, 0, 1. Plug them in, 1, 0, 1. But again, based on the restriction, we can't use 1. So that's going to be undefined. And then we look at the last function, 2 minus x for anything greater than or equal to 1. So x and y equals 2 minus x. And x greater than or equal to 1. So we'll start at 1 and just go greater than. Plug them in. 2 minus 1, 1, 0, -1, -2. And we can use all the points on that one. Okay. And then when graphing, let's see, I went 4 to the left, 1, 2, 3, 4, 4 to the right, 1, 2, 3, 4. And then the highest I went was 3, 1, 2, 3, and the lowest I went was 2. All right, if I'm graphing the first function at -1, 3, we're going to have a point that's undefined, so it's going to be an open circle. And then -2, 2 will be closed. -3, 1 will be closed all the way down that way. And then for the next function, we have -1, 1, which is right here, be closed, and then 0, 0, and then 1, 1, which will be open. So we look like that. And then the very last piece, we can use all these points. We're at 1, 1, which we can use, which means that this point gets filled in, which means that this point becomes defined. So 1, 1, 2, 0, 3, -1, 4, -2, and there you go.
It was just, I think, the last question, which is when f of x, what is it? Yeah, when f of x does not exist and x approaches a, that's the part I got stuck on. I didn't know what it was asking.
Graph. Okay. Use the graph to determine the values of a for which the limit does not exist. Oh, okay. So this is asking you at what value of x do you think a limit doesn't exist? So let me actually label these values. This is -1, and that's 1. So looking at this graph, where do you think that a limit wouldn't exist at? -1 or 1?
-1.
-1. And why is that?
I think you have one of the points open.
Well, the point being open has nothing to do with it. The point being open just says that that point's undefined. But I guess a better reason could be stating that, is there a break in the graph at -1?
Yes.
Yes. Which means that if you analyze this by limits, the limit from the left would be, so if you approach 1 from the left, that would be approaching 3. If you approach -1 from the right, we would be approaching 1. So now if we asked, does an actual limit exist at -1? Well, if the limit from the left is 3 and the limit from the right is 1, do we have a limit from both sides?
No.
No. So we would say the limit as x approaches 1 from both sides does not exist. So this means all this wants to know is that value of a is going to be 1, because that's where it doesn't exist. That's where you won't have a limit.
So the answer would be
just 1.
Just
type
one?
in 1. Yep.
Freaking knew it. Thank you, sir.
Yep.
Oh, wait.
What else?
Oh, that's not the question. That's not the answer. Do you type in D and E, and then 1?
Oh, sorry, not 1. What should that be? Should be -1. My bad.
Oh,
Forgot the sign on those. -1. There you go. -1.
Okay. Yeah, good.
There you go. Oop, where'd my chat go? There it is. All right. Any other questions, guys?
I had a question on 1.4.
1.4, James. Let me go look.
Kind of like question 18 and 19. You have like trig functions on the top, on the numerator and denominator.
Mm-hmm.
So I was looking online at some other stuff, and so we know that, like, so for example, the sine 3 of x over 3x would be 1.
Mm-hmm.
All right. So if it is that the same principle as like 3x over sine 3 of x is also 1?
Well, you want to make them into 1, right? So you have to manipulate them to become 1.
I was saying, like, say the trig function is on the denominator.
Yeah.
3x over sine 3x.
Yeah, sine 3x over, like it's in the numerator, right? You said? Or the
No,
denominator?
I got that one. So say the 3x is on the numerator and sine 3x is on the denominator.
Oh, then that would definitely be 1 because they have the same value.
Okay, that's what I was saying. So for, say, like number 18, where you have a trig function in the numerator and denominator,
Mm-hmm.
I had seen like a video, and I guess kind of threw me off the way he explained it, like the steps, where at one point you multiply, like, so it's sine 5x over sine 7x multiplied by 5.
Okay, so good. So remember, in all of this, we need to figure out how to make this trig expression or this limit look like this, right? What we're used to, that trig identity. Sine x over x is equal to 1, right?
Yes.
So we need to figure a way how to do that. So one of the ways to do that is to split this limit up. We can rewrite it as the limit as x approaches 0 of the sine of 5x times the limit as x approaches 0 of 1 over the sine of 7x. So now I ask you, how could I make this sine of 5x look like that expression? What could I multiply by?
Sine of 5x.
5x.
5x. Yeah. So we would multiply this one by Let me see. Give me a little more room. I'll just erase this one for right now. So you're going to multiply this one by 5x over 5x. And then the next one, let me rewrite it back, of 1 over sine 7x. Now this one is going to have to look like this trig expression. X over sine x equal to 1. So that's going to have to look like that. So what could I multiply the second limit by?
7x.
Good. 7x over 7x. Okay. And now we can move on and we get the limit as x approaches 0 of 5x sine 5x over 5x times the limit as x approaches 0 of 7x over 7x sine 7x. And we know from our expressions that this piece and this piece will become what number?
1.
1. So you got 1, 1, and all that's left over right now is the limit as x approaches 0 of 5x over, basically 5x over 7x. Because there's a 5x up there and that's 7x down there. Which means our x's will
Go to 1. Yeah.
cancel. Which means our final answer is just what?
5 over 7.
That's it.
And it's the same principle if you have like tangent over 3x over sine over 4x.
Exactly. You would do the same exact methods. Although we can save you some time because math is great. Here's option 2. The limit as x approaches 0 of sine 5x over sine 7x. And in this problem, we multiplied by 5x and 7x, right? So what's to stop us from doing it in the beginning? Nothing at all. I'm just going to multiply the numerator by 5x over 5x. And I'm going to multiply the denominator by 7x over 7x. And this becomes the limit as x approaches 0 of 5x sine 5x over 5x over 7x sine 5x, no, 7x over 7x. And just like we said before, those become 1s. And that leaves me with the limit as x approaches 0 of 5x over 7x, and boom. However you want to go about it.
Awesome, thank you.
Mm-hmm. Oh no. Okay. That was fun. Okay. What else? Any other questions?
Is there any way I can get in a breakout room with Ryan?
Sure. Anything to get rid of Ryan.
Hold on, I have to get on my laptop then. So give me just a sec.
Okay. Let me know when you're ready. For now, I'm going to post the notes we're covering today. Cal 1, we're doing continuity, right? Are we on 1.5 today? I think so. Yeah, we did 1.4. Okay, here
Let's
is,
see.
there you go. All right, I just posted the continuity PDF in the chat if you didn't download it already.
Hey, I have a brief question.
What's up?
So for homework due today, I'm looking at numbers 2 and 3 as examples, and I'm wondering, and 4 as well, and I'm wondering, like, I'm not fully sure how to represent some of these on paper, because for the most part I'm looking at the graph and just entering the numbers that I have here. Do you want me to just write these down? Can I skip them on my note?
Which homework is that?
For 1.3.
1.3. Let me see. It's the very last ones you said?
No, for like 2 and 3 as examples.
Oh, sorry, 2 and 3. Let me go.
So like you just look at the graph and then you just fill in whatever the information is.
Oh yeah. So yeah, 2 and 3. Just, I mean, like it says, just give me the limit notation, like limit equals 3, limit as x approaches 2 equals 1. You don't have to draw the graph unless you want.
Okay.
To. Yeah.
Alrighty. I was gonna say, because I was like, am I just gonna write down 1a is 3, 1b is 1, and so on and so forth?
Yeah. Just write the limit notation. It's good practice.
All right, you can send the me's wherever you need me.
All right, breakout room, create, assign manually, 1, and then assign to who? Let's see, Ryan's going, and who has to go?
Me.
Steven, right? Yeah, Steven, right?
It's in my laptop too. 2s.
Oh, Ryan's laptop. Okay, there you go. All right, Ryan and Steven, and bam, goodbye.
Oh
no. Oh no. Okay, cool. So we get into continuity today. Yeehaw. Good stuff. So we're just going to discover why functions are continuous and discontinuous using limits. And the only way to practice these rules is to really just look at discontinuous functions, because looking at continuous functions is just way too easy. All right, so there are 3 rules to continuity. So the first rule is that to be a fully continuous function, the point must be defined. F of A must be defined. Step 2, or rule 2, the limit at x as x approaches A must exist. And rule 3, the limit value must equal the point value. So we must pass all 3 rules to be a fully continuous function. If we fail one rule, it throws the whole thing out and the function is discontinuous. So today we will practice the rules of continuity. We will discover what it means to be discontinuous and maybe what it means to be continuous. Okay, so looking below, this is the graph of a continuous function, meaning that there are no breaks in the graph, there are no holes in the graph, everything exists. So this would be a continuous function, which again would be way too easy to use the rules of discontinuity on. Now, if we look below, this is what a discontinuous function looks like. Look how much fun that looks. My goodness, that looks way better than the one above it, right? Look at all the breaks and holes in this graph. So, using the rules of continuity above, we want to explore this graph and see why and where this function is discontinuous at. And reading from left to right, what x value do we look discontinuous at? First.
3.
1. How about 1?
1. That's what
1. I said. Okay. So let's go ahead and look at that. So let's analyze this. I'm going to say x near 1. And in order to analyze this x value, we're going to use limits, of course. So let's go ahead, since we're analyzing this near 1, let's go ahead and give it a y value. Let's just say that this is going to be, I'll go with 2. Why not? Okay. So we're going to look at one of the first rules. Actually, yeah, the first rule is the point defined? So for rule 1 of continuity, If I said, what is f of 1, what would you give me?
It's not there.
It's
Does not
undefined,
exist.
right? It's undefined. And based on the first rule of continuity, the point has to be defined. So is this a fail?
Yes.
This is a definite fail, which means if you fail one condition, if you fail one rule, it throws the whole thing out, which means that this function is definitely discontinuous at 1. But I want to further look into it by just using limits, right? So step 2 would be, does a limit exist? And in order for that, let's go ahead and look. Well, actually, let me write this down first. The limit as x approaches 1 from both sides of this function. So using the graph above, as we approach 1 from the left, y is getting closer to what value?
2.
2. As we approach 1 from the right, y again is getting closer to what value?
2.
2. So this means if the left-hand limit is 2 and the right-hand limit is 2, this means the limit from both sides must also be
2.
2, which by the rules of continuity would be a pass. But does that matter anymore?
No.
No.
No, because again, if you fail one condition, the whole thing becomes discontinuous. And since we failed rule number 1, we will state that at x equals 1, f of x is discontinuous. Discontinuous. There we go. Okay. So once again, the reason we're doing this is we are practicing the rules of continuity. So let's go ahead and look at the next x value that looks where we might be discontinuous at. And Amanda, you said what number?
Well, I said 1, but I think you're looking for 3.
Good. All right. All right. You said 3 the second time. Good. All right. So we're going to look at 3 because we have a y value, well, an undefined y value up there, and we have a defined y value down here. So once again, let's go ahead and give these y values, or give these points some y values. So I'll just say that down here is -1, and over here, we'll just say that this is 3. Why not? Okay, and we analyze again. I'll say x near 3. And rule 1 asks us if a point is defined. So if I say f of 3, what would you give me as the output?
-1.
Good. -1. Because we always state the defined point. Even if there's an undefined point up here, we always state the defined point. So, hey, we have a point that is defined. That means we have a pass. We are looking good, aren't we? We passed rule 1. Now we move on to rule 2. We want to know, does the limit as x approaches 3 from both sides exist? So now let's look at this. So as we approach 3 from the left side, y is getting closer and closer to what number?
-1.
-1. And then as we approach 3 from the right side, y is getting closer to what number?
3.
3. So the left-hand limit is -1 and the right-hand limit is 3. Therefore, do we have a limit from both sides?
No.
No, because the left hand does not equal the right hand. So our limit does not exist, which means we fail. So we failed rule 2, which means it throws the whole thing out, which means that we can state that at x equals 3, f of x is discontinuous. I'll just abbreviate it. F of x is discontinuous. Okay. Once again, all we're doing is practicing how to use the rules of continuity. Any questions so far? And now, let's go ahead and look at the last x value where there might be a discontinuity. And what x value is that?
5.
5. Good. So we'll say x near 5. And of course, we'll say that that's 2, whatever. And then this one we'll say is 4. Okay. So rule number 1, what is f of 5? So when x is 5, what's our output?
4.
4.
4. Good. That's a pass. Yeah. 2. What is the limit as x approaches 5 from both sides? So if we
2.
approach, what was that?
2.
2.
Good. Because if you approach 5 from the left, y gets closer to 2. And if you approach 5 from the right, y gets closer to 2. So the limit from both sides is 2. Oh my goodness. So close. We have a pass on both, right? And then 3. We are going, so this is the third rule of continuity. The value of the limit as x approaches 5 must equal the value of the point. Well, what is the value of our limit?
2.
2. What's the value of our point?
4.
4. Oh, do those equal each other?
No.
No. So guess what? We again fail. We were so close, right? So close. We fail, which means it throws the whole thing out. And once again, we are discontinuous. At x equals 5, f of x is discontinuous. And that is how you practice the rules of continuity. See, isn't it way more fun to be a discontinuous function? Yeah, sure. All right, cool. Okay, any questions on that page? Be safe. Yeah. Okay, let's move on then. Okay, so the next 2 pages are just going to go over what types of discontinuity we have, something such as removable discontinuities, jump discontinuities, and infinite discontinuities. So the first one, like I said, just to make this really simple and I guess fast. So this is called a removable discontinuity because 1, we start off with a rational function. So we're given x squared minus x minus 2 over x minus 2. So if you were to find the domain of this function, the domain of this would be x can't equal 2. But then you notice you can factor the numerator. So if you factor it, we would get x plus 1, x minus 2 over x minus 2. And our x minus 2's would cancel, giving me a new function x plus 1. But I have a question for you. Even if we cancel out the denominator, do we still have to abide by the same domain?
Yes.
Yes. Good. So no matter if you reduce the function, you still abide by the original domain. So here would be our new function, but it's still going to be considered a discontinuity, only a removable discontinuity, because we remove the part where it wouldn't exist, but you still have to abide by the domain. And if you check this by the rules of continuity, well, we would already fail rule 1, wouldn't we? Rule 1 says, well, what is f of, where are we at? 2. What is f of 2? And is a point defined when x is 2?
No.
No. So that would be a fail, meaning that yes, this is a discontinuous function at x equals 2. Okay.
So that's to be specific, like at x equals 2, because if they give us like x equals 1, then it's continuous. Like
For
that
sure.
specific point, yeah.
Yep. So yeah, so like I said, if we were looking at 1, oh, this would be fully continuous because the point's defined, the limit would exist, and the point value and the limit value would be equal. So yeah, we are basically looking at specific values of x. Okay. All right, so there's that one. Next is the piecewise function, which we come across in infinite discontinuity. So we are given f of x equals 1 over x squared if x cannot equal 0, which is given because 1 over x squared is a fraction and we can't have 0 in the denominator. But then we're given a point that says when x is 0, y is exactly 1. So this point is reflected exactly right there by the piecewise function. Okay, so if we were to use the rules of continuity on this, we would pass rule 1. So the first rule of discontinuity says, what is f? So we're going to explore 0 here, of course. So if I said, what is f of 0, what y value would you give me?
1.
1, which is a definite pass. And then we would have to move on to rule 2 for our limits. So I'm going to write both out here, though. The limit as you approach 0 from the left of f of x, and the limit as you approach 0 from the right of f of x. Okay, so let's look at the left-hand limit. If you approach 0 from the left, where is this tail going?
Infinity.
Infinity. Good. And then if you approach 0 from the right, where is this tail going?
Infinity.
Infinity. But since we're only on continuity today, yes, the left hand's infinity and yes, the right hand's infinity, which means we don't know any better yet. And since I'm the only one who can count to infinity, you guys are going to have to state that, well, guess what? Since the left hand limits infinity, the right hand limits infinity, and nobody has any idea what infinity is, the limit does not exist. Because if you honestly think about it, will those tails ever meet up? Will they ever come to a stopping point?
No.
No, which means we have a fail. You guys jealous that I can count to infinity?
Super.
All right. Okay. So that's a fail. It throws the whole thing out. And this means that at x equals 0, f of x is discontinuous. And it's called an infinite discontinuity because the tails head towards infinity. Okay. So this is using rules of continuity and going over different versions of discontinuity. Everybody good with this page?
Good.
Good. Okay. And then the next page. All right. We have another removable discontinuity, and we have a jump discontinuity. All right. I want you guys to take probably about 5 minutes and go ahead and try out number 3 and number 4. So try to prove why these functions are discontinuous. And for number 3, yes, you're going to want to explore at x equals 2. For number 4, you're going to have to pick an x value yourself and explore why it's discontinuous at that x value. So go ahead and try these out.
Ooh, that function. Gross.
Yeah. All right. There's 3 and 4, y'all. So for number 3, we again see it's discontinuous, not only by the graph, but by the rules of continuity. The point was defined, the limit existed, but then 3, the value of the limit did not equal the value of the point, so we had a fail. And then 4, if you don't know what that function is called, it's called the greatest integer function. And you could have examined everything at 0, 1, 2, or 3, whatever values you were given on there. And no matter where you examine this function, you would see that the limit does not exist at any of those integers. So I examined 1, therefore I said at x equals 1, the function is discontinuous, but truthfully, at every single integer, the function is discontinuous. So any questions on 3 and 4? So hopefully by now, you know how to work the rules of continuous, or the rules of continuity. There you go. I'll leave that up for a second. All right. Everybody feel good about it? All right, got thumbs up. Woo! All right. Let's move on then. Last, no, not last page. That's the last page. Here's the other page. Ha! Okay. So for continuity properties, basically what this says is that in order to know where a function is continuous, then you must know the type of function you have and the domain of that function. So if you know the domain of a function, you know where a function is continuous at. So for A, it says a constant function, f of x equals k, where k is a constant, is continuous for all x. So a good example for A, let's just say f of x equals 5. So this is a constant function. Remember, a constant is a number without a variable. If I were to graph this, it would be the graph of a horizontal line, because f of x equals 5 is the same as y equals 5. So it would be the graph of a horizontal line. And we see that the tails, one tail goes to negative infinity and the other tail goes to positive infinity. So we know the domain of a constant function is the set of all real numbers. So negative infinity to positive infinity. But in terms of continuity, we would say that this function, based on its domain, is continuous for all x, right there. We are continuous for all x. All right. And then B is for power functions. For n, a positive integer, f of x equals x to the n is continuous for all x. So remember what it means to be an integer. An integer is just a whole number. But for these power functions, it has to be a positive integer, meaning we need positive whole numbers. So to represent B, I can just keep it simple and say f of x equals x squared. Doesn't matter if it's x, x squared, x cubed, x to the 100th, it will still be continuous for all x because we know the domain of these type of power functions is still all real numbers. Okay. And then C is basically a consequence of A and B. C says a polynomial function is continuous for all x. So if you have a polynomial, you are continuous for all of x. And actually, let's just use an example below. But before I continue, what does it mean to be a polynomial function? What is one of the main things you need to know in order to be a polynomial function? And it has to deal with exponents.
Ooh, pick me, boss.
Ooh.
But it's a squared function?
Well, being a polynomial doesn't mean you're squared. A polynomial can be to the first power, the second power, the third power, the 100th power, the 500th power. So I'm just looking for a basic definition of what it means to be a polynomial.
They're all positive integers?
What are?
The leading one?
Not just the leading one.
All powers of x.
All powers of x. To be a polynomial function, all of your exponents, your degrees, your powers, whatever you call them, have to be whole positive numbers. So that's what it means to be a polynomial. Your exponents must be positive integers. So B would actually be considered a polynomial. A would also be considered a polynomial, but A is called the zero polynomial because you can rewrite it as 5x to the 0th. And 0 happens to be an integer, but it's neither positive or negative. That's why we call it the zero polynomial. Okay. And then to get an example of C, I think I have an example down below. For a polynomial function, look at that. Number 5 down below. F of x equals x to the 100th minus 2x to the 37 plus 75. Are those exponents positive and whole numbers?
Can you scroll up just a tad?
This way, right?
Yes, they are positive and whole numbers.
Good. So all the exponents are positive whole numbers, which means that if you are a polynomial function, your domain is all real numbers. But since we're talking continuity-wise, we say that for any polynomial function, we are continuous for all x. All right. Perfect. All right. So A, B, and C are basically exactly the same. They're all polynomials. They all have the same domain, and they're continuous for all values of x. All right. D, a rational function is continuous everywhere except values that make the denominator 0. And we have an example of a rational function down below. Yeah, I can just zoom out a little bit. There we go. So we will use number 6 as an example for our rational function. Okay, so look at this denominator. What is my domain going to be? Or what's easier to say? What x value should I avoid for this denominator?
1.
And what else?
-1.
-1.
-1 and +1, right? Because if I plug those values into the denominator will become what number?
0.
0. Good. Now, if we're stating it continuity-wise, we will say that this function is continuous on, and let's go ahead and state intervals. How do I write -1 and 1 in interval notation? Where do I start?
Negative infinity.
Negative infinity to -1, union, where?
-1.
-1.
And then 1.
And then
union infinity. Oh, wait, I mean 1 infinity.
There you go. So again, if you know the type of function you're dealing with and you know the domain of the function, then you know where you're continuous on. Okay, cool. And then for E, there's no example for E, so I'll just move back up here. So for E, it says, for n, an odd positive integer greater than 1, the nth root of f of x is continuous wherever f of x is continuous. So for E, we're talking about odd roots, such as the cube root, the 5th root, the 7th root, any odd root. So for E, a good example, here, let me zoom in a bit. There we go. So for E, we can say f of x equals the cube root of, let's just say, x. And here we have to figure some things out about the cube root. Well, one thing we know is, can we take the cube root of a positive number? I'll write this as an example. Can I take the cube root of 1? What is that?
1.
1. Can I take the cube root of 0?
No.
Tricky. The cube root of 0, guys, is
0.
0. And then the last part, what is the cube? Can I take the cube root of -1? Or
Yes.
any
No.
negative number?
No imaginary numbers.
That's only if it's what type of root?
Ah, man, I forgot.
Square root.
An even root, such as the square root. Good. No trick questions here, right?
Mm-hmm.
So if we're given the cube root of x, then if I can take the cube root of negative numbers, positive numbers, and 0, what is my domain?
All real numbers.
All real numbers. Because what that's telling us is that I can use any number I want, right?
Oh, yeah.
There you go. But that is just for a basic cube root of x, right? So by the definition, it says we are continuous wherever the inside function is continuous. So let's say we had another example, such as the cube root of 1 over x. What would the domain of this function be? Well, what's the only number we couldn't plug in?
0.
0. So my domain would be -infinity to 0 union 0 to infinity, only because it's a fraction on the inside. So again, by the definition, the cube root, or not even the cube root, the odd root, because I can replace these with 5 or 7 or 9, whatever odd number I want. The odd root is continuous wherever the inside function is continuous. Does that make sense? All right. Kinda, right? So it all depends on what's inside the house. That's all that matters. So whatever you have inside, you're going to have to find out what that domain is. Okay. All right. F, I'll make an example of F before we move on to the next one. So for F, now F deals with even roots, square root, 4th root, any even root. So it says for n, an even positive integer, the nth root of f of x is continuous wherever the inside function is continuous and non-negative. So once again, for example, let's go ahead and make up an even one. And I'm going to keep it simple. I'll say the square root of x. And does anybody know what the domain of the square root of x is?
Would it be all real numbers?
Not
0 to infinity.
good. 0 to infinity, because we know
it
we
can't
can
be
take
negative.
good. We know we can take the square root of positive numbers. We know we can take the square root of 0. But if we take the square root of a negative number, we get what?
I, or imaginary number.
I or imaginaries, right? So this means that the domain for an even-rooted function based on the inside function, the basic domain would be 0 to infinity. Why the bracket on the 0?
Because it cannot, it can only equal 0. It can be greater or equal to 0.
Because
there you go.
the bracket, good, because it's greater than or equal to 0, and because you can take the square root of 0, right?
Yeah.
So this works for any even root. Okay. But again, just to show you, it all depends on the inside function. What if I was given the square root of this time? Again, what if I said 1 over x? What would my domain be now?
It would be 0 to infinity.
Good. It would still be 0 to infinity, but what's going to change?
It wouldn't be the bracket.
Good. Because it's in the denominator, which means we can't allow 0 in the denominator. Therefore, it gets a parentheses. Yeah. Whew. All right. And then G. A trig function is continuous at every number in its domain. So I'm not even going to give an example of that. I think I have an example of it down below, but you guys saw trig functions last semester, so hopefully you remember all their domains, right? Yeah, sure, right? Or just Google.
Almost. Yeah.
That long silence was so comforting.
I know. It's always good. Like trig, we had to remember trig. You'll be all right. You're in front of a computer, right? Okay. And I'll get to this theorem in a second when we get to number 8, because that theorem deals with composition functions and limits, and number 8 is a definite composition function. Okay, but for number 7, let's go ahead and find the domain of this monster right here. So for this guy, well, you have the square root of x plus x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. So let's go ahead and pick this apart. We're going to have multiple domains. So let's start with, I'll zoom in. Let's start with the square root of x. This is given. What's my first domain going to be? I'll say domain 1.
0 to infinity.
Good. 0 to infinity. Good. 0 to infinity. And then let's look at the next piece. What is the domain of this fraction going to be?
1 infinity.
Think about it. What number cannot be in that denominator?
1.
1. So you had the first part right, but we're missing a piece. If you can't choose 1 but can choose any other number, what's it going to be?
Negative infinity to 1 and 1 to infinity.
Good. And then I guess we have a domain 3. We don't really need this one, but I'll write it. What is the domain of that piece?
Negative infinity to infinity.
Oh, good. Why do you say that?
Because it doesn't matter what you put in the x, as long as you square it, it'll be positive.
Good. So what you're saying is that this denominator will never, ever become 0, right?
Right.
Good. And you're right. Or maybe I'm right. I don't know.
Well, you did teach me, so.
Good. Okay. So now we have 3 pieces to the domain. So we have to create one domain only from all 3 pieces. So looking at this, in order for, if we were going to plug a number in, it has to work for all three parts. So one thing we know is that we can plug any number into this piece. So we don't really care about that. But then we have to worry about these two. What can I only plug into the square root?
Positive numbers.
Positive numbers. So which piece of domain do we get rid of with that?
That negative infinity.
That negative infinity to
infinity.
Well,
Or
right here.
to 0.
Right? So right here, we get rid of a piece of it, right? Because we know we can't use negative numbers. But what number could we actually start at for this?
0.
0. So we'll say bracket 0. And then where do we have to stop at?
1.
Oh, yeah.
1. And that gets parentheses. And then where can we continue from?
1 to infinity.
1 to infinity. That's it. That is the domain of this function. That nasty looking function. So this is what it's continuous on. Let's say continuous on this. Good times. All right. Now the last one. Since it's a composition function, we'll use this theorem A and B basically on number 8. So what this theorem says is that if f is continuous at, I think that should say A, right? If you plug in g of A, you get f of B. No, it's fine. Sorry. If f is continuous at B, and the limit as x approaches g of x equals b, then the limit as x approaches a of f of g of x is equal to f of b. So basically, all this theorem is saying is that, hey, if you have two functions who are continuous at a certain x value or at the same x value, then this means you can take the limit and apply it inside of the actual composition. So you can take a limit and apply it inside of the composition, as long as both functions are continuous. I wouldn't say at the same value of x, but at certain values of x, because what we're saying with this is that g of x is continuous at a, and if g of x is continuous at a, g of x becomes b, and in order for this composition to work, this means that function f has to be continuous at that value of b, therefore giving me f of b. But don't let that boggle your mind too much. Just know, all you want to do to take away from this property is if you're ever given a composition limit, you can go ahead and just take that limit and plug it inside the actual composition. All right. And then B says, if G is continuous at A and F is continuous at G of A, then the composite function f compose g is given by f compose g of x, means that the composition is continuous at A. So basically, we're just restating above, but in more algebraic terms. So if each function is continuous, then the composition of two continuous functions will still be continuous. Whew. All right. So number 8. Which means let's go and pick this apart because it's a composition function. So what are the two functions you guys see?
H of x and sine of x squared.
Well, not looking at that, looking at this composition. What two functions do you see?
I'm going to guess sine of a number and x squared.
That's it. So the two functions here are sine. So I'm going to say the domain of the sine of x. And the other function you see here is x squared. Because does it not look like we composed those two functions and got the sine of x squared? Okay. So what would the domain of sine be? What do you guys remember from that? What's the domain of sine?
Is it going to involve like pi and?
No.
Should be negative infinity to infinity.
That's it. Because does sine ever stop?
No.
No, right? It's a continuous wave from negative infinity to positive infinity. And now what is the domain of x squared?
Negative infinity to positive infinity.
Negative infinity to positive infinity. And when you compose these two functions, we get the domain of sine of x squared. Well, if both functions' domains are all real numbers, then the domain of sine of x squared should also be
all real numbers.
All real numbers. That's it. So this will be continuous for all x. There you go. Domains and continuity. If you know the function you're dealing with and you know the domain of that function, then you know where you are continuous at. Any questions on that page? Okay, let's go then. Now we're on the last page, all right? Last page. These are fun. So this says, for what value of the constant c is the function f continuous on negative infinity to infinity? So here is where we are going to connect limits with piecewise functions. So we want to know where a function is continuous on. So in order for a function to be continuous, we know that a point must be defined and a limit must exist. Well, if you look at this piecewise function, we have x greater than or equal to 2. So we can be equal to 2. Does this mean we're going to have a point defined at 2?
Yes.
Yeah, good. So if I said what's f of 2, all we know for now it's going to be defined, right? So that's a pass. That means we pass rule 1, which means we have to go to the next step and prove that a limit exists. So in order to prove that a limit exists, we have to prove it by using a left-hand limit and a right-hand limit. So here's what we're going to do. We'll call this 2a. We're going to say, what is the limit as x approaches 2 from the left of f of x? And now here is where we match limits to the restrictions in a piecewise function. So I want the limit from 2 at the left. And if you ever have a limit from the left, does that mean that our x values are less than, or are the x values greater than the number you are approaching?
Less than.
Less than. So good. So that is based on the definition of a limit from the left. If you ever approach a number from the left, you are always less than. And if this limit matches to that restriction, this means we get to use which function in the piecewise function?
The top one.
The top one, the first one, right?
Mm-hmm.
So we will write it as here, cx squared plus 2x. And now all we have to do is plug in what number?
2.
2. That's it. Ew. There we go. And I'll get 4c plus 4. So let's go ahead and save that. That is the limit from the left side. Now let's get into 2b. The limit as x approaches 2 from the right of f of x. And again, match your limit to your restriction. If you approach from the right, then this means we have to be less than or greater than?
Greater than.
Greater than.
We're going to be greater than. And if this limit matches to that restriction, then which function do we get to use?
2, positive 2.
Well, what function?
Oh, I'm sorry. The x cubed minus cx.
There you go. And now you get to plug in what number?
2.
2. There you go. You get 8 minus 2c. All right, here's the fun and exciting part, guys. In order for the limit to exist from both sides, we must set the left-hand limit equal to the right-hand limit. And since we have a left-hand limit and a right-hand limit, we take 4c plus 4 and set it equal to 8 minus 2c. See what we did there? So the limit from both sides, in order for it to exist, we set the left hand equal to the right hand, and we're going to solve for that value of c. So add that 2c to the left. I'll get 6c equals 4, and c equals what?
2 or 3.
2/3. And that's what we're looking for, guys. So the question said, for what value of the constant c is the function continuous for all numbers, for all real numbers? So what we're saying here is that if c is 2/3, then the piecewise function becomes fully continuous. Crazy, right? And if c is 2/3, then a limit would exist and we would pass, and then the limit value would equal the point value, and we would have a fully continuous function. But we don't have to go that far. We just have to show whatever the value c is that would make it continuous. Okay. Any questions on that? Got a thumbs up. Yeehaw. Okay. If you don't have questions on that, the last one is all yours. So go ahead and try it out the same way. You don't have to do the step 1 part, because what I did here, the defined and pass, just because you have a less than or equal to, greater than equal to, then we know we'll have a point that exists. So just go ahead and move on to the limits. All right. Hey, it's Ryan's laptop.
Wait, what?
Oh, you logged in as Ryan's laptop.
Yeah.
Cool.
All right.
Yeah, all right, cool. Oh, yeah. This one, all yours, Ryan.
Oh, good gosh.
Okay,
Yay.
I'm sorry I'm late to this, but I was looking over what we had. How come we didn't do the third part where we verified that the limit is the same as the function of that number?
Did you not listen to me?
I'm sorry. My daughter was in here screaming for candy, and my husband took my son to gymnastics. So no, but not intentionally.
Okay.
Couldn't.
Oh, good. So, like I said, we really didn't have to do number one, but I showed step one of like why we move on to the limit. So we want to know that if a point exists, we can move on. And all this problem wanted was to find a constant c that would make it fully continuous. So we don't have to go on to show the next step, because if c is 2/3, then no matter what, this function will be fully continuous.
Okay, that makes sense. Because if we put in 2/3, then there will be a defined point.
Exactly.
Correct? Okay.
There will be a defined point. There will be a limit that exists, and the point value would equal the limit.
Thank you.
And now everybody's trying out number 10, or pretending to, and making and making Ryan do it.
Let's see.
This might be a bad question, but on the first step, I hope so. But like basically with the x, you know how it says x is less than 2? Are we still like allowed to use the number 2, or we just have to?
Yeah, you're still allowed to use number 2, but you have to be careful with that one, because what happens if you plug in 2?
It's gonna cancel everything.
What do you mean by cancel everything?
Oh, well, I did it.
You'll get 0/0, right?
Yeah.
So that means look back at it, and what can you do to the numerator?
I guess I could replace it with another number, like 1. Or...
No, we don't replace anything. X squared minus 4 can be what?
X squared minus 4. It can be simplified, or basically you can group it.
So you can factor it, I think is what you're trying to say.
Factor. Here we go. Yeah. Oh man, I'm rusty.
So factor it, and then simplify it, and then plug in 2.
Oh, perfect. Yeah, it makes better sense like that.
Because if you don't, then you're not going to get anywhere with this problem.
Yeah, it's going to be 0.
Yeah, because this problem's longer than the one above it, because you're going to need a limit from the left and the right at 2, and a limit from the left and right at 3 before moving on.
Yes.
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 Oh, Sean Connery died.
It's so 2020, bro.
Yeah. Now it's Screech. I didn't see that coming.
Screech is dead.
Wait, he died?
Yes,
Yeah.
Screech is dead.
Oh, I saw that he had like cancer, but I didn't know he died. Man, that's
Yeah.
my childhood right there.
Wasn't he like a monster jerk or something?
Oh yeah,
he came
was
out pretty weird.
Yeah, as an adult, he was pretty icky, but I mean, he was Screech. Don't say about the bell. They still run refunds on that.
Screech. Everybody else is like, who's Screech?
Yeah.
All right, a little late, guys. Okay, cool. Someone joined my business cal class that's supposed to be tomorrow. Marvelous. Work it, work it, work it.
Is that you playing Monster Hunter?
No, it expires tomorrow, right? Or something like that.
Oh, it does? Oh, no.
I think so. Oh, yeah, let me stop sharing my screen. Boom.
Oh, I'm still working mine in secret.
Yeah. I'm going to stop that one. I guess I'll write it on my notes too.
Yay. Not gonna lie though, that was like the most fun I've had playing a Monster Hunter game though. Such a good time.
Oh yeah, I was on mute. When you took down the Rathian?
Yeah.
You did that by yourself or with other people?
No, I did it by myself.
Dang. How long did it take?
Not that long. Yeah, I think I knocked him out and that like other smaller monster out within like 10 minutes.
No way.
Yeah.
You really figured out that thing then.
Yeah.
Huh. That's cool. Guess I need to switch from Hammer Guy, huh?
I don't know. I happen to like never played Hammer.
Well, it sounds like you would master it.
Nah. Not
Nobody
my cup of tea.
Nobody wants to master the hammer.
Just you.
Just me. Hey man, I just like to flip in circles, okay?
Launch yourself off ledges.
Lounge.
Lounge.
There weren't even ledges to do it from. So I think when you jump off the cliff the first time, there's just a place with a hill, and that's when he does it.
Does he just land on the hill?
Yeah.
This is not as awesome as I was hoping it to be.
Nope.
Hey, Professor.
What's up?
So for the homework of 1.3, a lot of it is just looking at the graph and plugging it into a calculator. So to show work on that, how would you want us to do that?
If it's that simple, I guess at most just write your answer down. Like you said for 1.3?
Yeah, for a lot of the problems on 1.3, like for example, number 12.
Number 12.
It just like shows a graph and it's like
okay. Like once again, just write the limit notation and put the answer next to it. That's it.
Okay.
Yeah.
Right, thank you.
Mm-hmm. $10A minus. Yeah.
Aw, dang. You're right where I am.
Yeah, we're going. We got 10 minutes left.
10A minus 4B equals 0?
Yep. No, not 0. 3.
What? Oh,
right?
yeah. Yeah. No, I made a boo-boo.
Boo-boo.
6.
And once you guys have your limits from the left and right on 2 and 3, the next thing you're going to do is create a system of equations to help you solve for A and B.
Solved by matrices. Yay!
Oh gosh. How do you use Gypsy?
They didn't put that back. No, don't be playing with that.
Jesus.
Put it down.
There's a bomb in there. Sorry. Loud.
It was if I am you, then if you are me, then who am I? Forget how it works.
Ugh.
You're sniffling too.
Me?
Right? Or no?
Yeah. No.
Hey, look at that. 1/2 and 1/2. Bingo.
Let's see.
Oh, fine.
Checking it by
I'll share my screen then. All right, fine.
No, I'm doing my matrices, bruh.
I'm not gonna show them matrices. Bingo. There we go.
A transpose.
Get out of here. Transpose.
Oh wait, no, I don't want to do transpose. I want to do.
All right, y'all. There it is. Breathe it in. So you get your equation for the limit at 2. Then you get your equation for the limit at 3. And then you put them into a system of equations and you solve for A or B. And you get that A is 1/2 and B is 1/2. So let me know if you got stuck or have any questions on it.
I'm sorry, that last part doesn't look familiar to me. I got the right equations. I just don't know how you did that last part. I'm so sorry.
Okay. Oh, the system of equation?
Yeah, I don't know how you combined them or whatever. Sorry.
Gotcha. All right. Well, Ryan, you have your screen up. Go over solving a system.
Oh, okay. All right. So the easiest way to solve system of equation is by elimination. So just as the name suggests, I'm looking to eliminate one of my variables. Looking at this system of equation, B is going to be easier to eliminate because if I multiply this second equation by negative B, or sorry, negative 2, my new system will be 10A minus 4B is equal to 3. And then my second equation will be negative 8A, and then negative 2 times negative 2 is a positive 4, plus 4B is equal to negative 2. Now I just add my two equations together. 10A minus 8A is 2A. 4B, negative 4B plus 4B is 0B. And then 3 minus 2 is 1. Solving for A, we get A is 1/2. Now this is one of the solutions, but I'm still missing my second solution, which is B. So to find B, I can take my solution for A and plug it into either of my equations in my system of equation. So between equation 1 and equation 2, which equation looks easier to deal with?
1.
1?
Like
All right.
the top one?
Sure. Yeah, so that means I'm going to let A equal 1/2. So this implies that 10 times A, so 1/2, minus 4B is equal to 3. So 10 times 1/2 is the same as 10 divided by 2. So this is just going to be 5 minus 4b is equal to 3. Isolate the term that has my unknown. So I'm going to subtract 5 to both sides. So negative 4b is equal to negative 2. Solving for b, I'll divide negative 4 to both sides, and we'll have b is equal to 1/2. And there are 2 solutions.
Perfect. Thank you so much.
Sure.
Yay. I see your video game, Ryan.
No, I'm just kidding. I could care less.
Uh-huh.
Now you guys know what I do when I'm in lecture.
He's making money. He's grinding.
Yeah.
Grinding.
We already knew that, Ryan. It's okay.
Pays more than this job.
Sure does. Keep grinding. Okay, y'all. Well, that's it. That's continuity. So if you have any questions, ask. Other than that, we are done.